Hi guys, I'm Anna. Unfortunately I was ill last week so I couldn't do the lecture. But yeah, generally last week you guys should have covered some of the introductory theory in terms of randomized control trials. And hopefully started understanding why we conduct them or why they create the perfect experiment and things like that. And so today we'll be going through an example of what I found, or not what I found, in the randomized control trials that I've been introduced to over the last term, this one was the most interesting one and sort of the easiest one to explain. So we'll go through an actual implementation of a randomized control trial. But yeah, and then we'll talk about the issues behind the conducting of randomized control trials and why in some situations they might not be appropriate. Right, so before we go into it, can anyone just tell me what the difference is between selection and sampling bias? Do we remember that from last week? Yep.
Actually, we had some questions about it. We were getting the two mixed up. We weren't really sure, so we left it on kind of a question mark.
Right, okay, so sampling bias is the bias. Okay, so when you're collecting data, what you're doing is you're creating a sample. And sampling bias arises from when the way you collect the data in itself is not random. Okay? So you've got a population, say you can divide it into, let's say, educated and uneducated. And you're just trying to see the effect on incomes of different levels of education. If you restrict yourself to just a portion of the sample that is mid to high educated, you're creating sampling bias because you're not creating a representative sample. Or if there's a way in which you go out and list the data in a certain way and you restrict yourself to the upper section or the lower section. And basically, it's if there's any process in the collection of data that is not random, which makes the sample that you've created unrepresentative of the population. Selection bias is bias that arises when your process might be completely random, but the individuals we're studying choose to do things. So they choose their treatment, which makes the assignment of treatment not random. Do we understand that? Yeah? So the way it was introduced to me was if you're looking at a health insurance trial, per se, and you want to look at the effect on health of either being insured or uninsured, if you make the process of assignment of insurance non-random, you just take it as it is, then you're going to get a disproportionate amount of people who are either more educated or more wealthy in the subsection of the or in the portion of the sample that you've collected, which represents insured. Because usually people who are more educated and more wealthy tend to have a higher likelihood of being insured. And in the population that's uninsured, you'll have people who are less educated and less wealthy. And that in itself has an effect on the health outcomes. So it's not just the insurance. Yeah.
So that means that selection bias occurs before you even sample.
Yeah. Unless you make the process of assignment completely random. So when you have a treatment, either insured or not uninsured, if you make sure that when you've collected the sample, after that you assign treatment in a way that's completely random, that's the only way of completely ruling out selection bias. Right. So moving on, the study we're going to look at today is a study done by Marion Bertrand and Sendil Mullainathan. I'm not entirely sure how to pronounce that name. But yeah, one's at Harvard, the other's at Chicago. And the title was, Are Emily and Greg More Employable Than Lakeisha and Jamal? Right. And it's a field experiment on labor market discrimination. So what they did is they replied to a number of employer ads with about 5,000 fake CVs, 4,870 to be exact, with names that are typically white sounding and names that are typically black sounding, for lack of more politically correct terminology. So we're classifying Emily and Greg as somewhat more white-sounding names, typically white-sounding, and Lakeisha and Jamal as typically African-American sounding names. Right, and what we're observing here is the callback rates. And so we'll use the data that they collected, and before we do anything else, we have to test for group discrepancies. So this is a randomized control trial, and this is a dummy variable randomized control trial. There are only two options. The name is either typically African American sounding or typically white American sounding. And what we're going to do is we're going to see if the characteristics that might affect the callback rates are equally distributed between the two groups. And there is one little surprise awaiting us in that. And we'll see if the process of randomization has actually created two basically equal groups. Right. One more thing about selection bias. Another way of thinking about it is that if you take the world as it is and you do the usual comparisons, a lot of the time selection bias results from the fact that you're not comparing like and like. In the real world, people who are insured and people who are uninsured are not, on average, exactly the same. You can only make causal claims when you say that the only difference between the two groups is the treatment that we've assigned and not anything else. And that's the issue. So over here, what we want to do is we want to say the CVs that we are sending are pretty much the same in terms of what employers look for, except for what the name sounds like. And then we'll look at whether or not there's a difference in callback rates. Right. Yeah, so I've pretty much explained that. We just want to test that the process of randomization has actually worked. And what we'll do to decide whether or not the discrepancies are significant is we're going to use hypothesis testing. Because before we start at all, the groups are going to have discrepancies. Any process of randomization isn't going to create exactly 50-50. It might be 51, 49, 52, 48, or something a little higher. But the only way we can pretty much tell whether the groups are significantly different is if we hypothesis test, which again has its margins of error, and that's what we're going to do with it. We're going to say at a 5% level, we're happy to accept 5% rates of error, and with that, we'll see whether or not we have discrepancies. Right, so what we'll do is we'll have a certain characteristic, and I've called characteristic theta, just to generalize, and we'll say that our null hypothesis, H naught, is that the mean, that's what mu is, the mean of theta for the group that's white is exactly equal to the group that's black. And our alternative hypothesis is that they're different, they're not equal. And this is pretty much equivalent to testing that the difference between them is 0, which is what the second line there is. That H naught is that the mean of theta with white minus the mean of theta in the group that's black is 0. And H1 is that the difference is not 0. Right. And the way we go about it is we calculate a test statistic, which assumes H naught, and then we compare the value of the test statistic to an underlying distribution. Right. So, yeah.
When you talk about a characteristic, the mean of a characteristic, if the characteristic was, for example, like level of education, how would you have the mean of a level of education?
Right, so the usual way to go about education is the number of years spent in either high school or college, depending on what you think is more likely to affect the callback rates. And this is where it comes down to the researcher to decide which of the variables is most likely to actually affect the outcome when we try to control for any of those. Right. So for testing differences in two sample means, we usually use what's called a student's t-distribution with, and this one is a bit weird to explain unless you have grounding in statistical theory. We use what's called a t-distribution with n minus 2 degrees of freedom, where n is your combined sample size. Over here, our combined sample size is 4,870, so n minus 2 is 4,870 minus 2. I don't want to delve too deeply into that. That's just what you use to test the difference between two means. It's a verifiable statistic. If you guys want, you can look at the actual theory behind it, but it's not particularly important. The level of, yeah.
Sorry, can I just interject for 1 second? Which is that we've covered normal before, and at that type of sample size, that's effectively a normal distribution.
Yeah.
And so just think of, in the picture you have in your mind, I would recommend just think of a normal distribution.
Yeah, so, yeah, I should sort of elaborate on that a little bit. The t-distribution, regardless of your degrees of freedom, pretty much resembles the normal distribution. So it's like that little bell curve centered around 0. But the tails at the end are slightly different. And the larger your sample size gets, the smaller the tails get, or not smaller, but the more the tails reflect the normal distribution. At sample sizes of, I think, north of usually even 120, that's when you pretty much assume normality. So with 400 or 4,870, we're okay with using the normal distribution. Right. Now, the test statistic is basically, you take the two means from each group, or your average, the average that you've calculated, subtract them, divide it by the standard error, or standard deviation, and you have your test statistic. You test it against the critical value, and then you conclude. Now, how do we do that? We say that, or for testing that the two means are not equal to each other, and one's not greater or smaller than, we're just testing inequality. We'll say that if the probability that our calculated statistic, the absolute value of our calculated statistic is greater than the value that gives us 0.05, then we'll conclude that the difference is significant. Do you have a question?
I'm just generally confused.
Okay.
Ask me something.
Basically what we do is we take our averages from the two groups for each characteristic, subtract one from the other, and divide it by standard error. That's our test statistic. If our test statistic is greater than a specified critical value, then we conclude that it's significant. Okay? And the critical value is given by our margin of error, our significance level, which is 5% at this point. The actual theory behind it is that if the probability that the distribution, according to the distribution, our test statistic would yield a probability of lower than 0.05, then it's a significant value. Perhaps this would explain it better. Basically, if our test statistic is either here, in this region, or there, in that region, we conclude that it's significant. If our test statistic is either greater than 1.96 or less than minus 1.96, it's a significant value. That's basically all we need to know for the next few parts. Is there anything else? Yeah, there's another very important part to go over. If our test statistic, however, falls in this region, the 95% region, we can't say that we accept the null hypothesis. We can't reject it, but we don't accept it. In a hypothesis test, not rejecting a hypothesis is not the same as accepting it. We never accept because we don't know. Okay? If we can reject it, that's almost definitive. Given our margin of error, we can say that it's significant. If it's not significant, it doesn't mean that we're accepting it. We're just saying that it's not large enough for us to have to redo anything. We can take it as given and move on. And the significance will come in evaluation when you say, this test was almost significant or not significant, not near significant at all. Right. Yeah, so this is just part of this lecture I was hoping would be in getting you guys sort of used to looking at statistical tables. And generally with statistical software, if you ask for a description of the variables that you're working with, this is the sort of stuff that you get. So what we have here is we have a variable called education, which takes on values of 0, 1, 2, 3, and 4, in which the values are as specified. 0 is no education. 1 is a high school, I think that's, yeah, high school dropout. 2 is high school graduate. 3 is they attended some college. 4 is they attended college, graduated, and perhaps attended master's programs and things. Right. Off jobs is just the number of jobs listed on the resume. Years of experience is number of years of work experience. Computer skills is a dummy variable, where 1 specifies that the resume mentions computer skills, and 0 is no mention of computer skills. And this is where a little surprise will be waiting us. Right. And call is our outcome variable. Call tells us 1 if the applicant was called back, 0 if they weren't. And this is what we want to examine. Right. So this is a summary, generally. And it's good to look at a summary of variables to see, first of all, what values they can take. So education takes a minimum of 4, a maximum of, or sorry, a minimum of 0, a maximum of 4. Off jobs, all applicants have reported at least 1 job, and the most reported has been 7. Years of experience, at least 1 year. The most is 44. Computer skills, because it's a dummy variable, nobody reports more than 1, because you either have computer skills on your resume or you don't. Same with call. And another 2 that we have are female and black. Black is our main causal variable, or the variable that we think is a causal variable. So black tells us either they have a typically black sounding name or they don't. 0 is they don't. They're typically white sound. Sorry, the CV has a typically white sounding name, and 1 is a typically African American sounding name. Female, 0 is male, 1 is female. Right. Moving on. So when we first look at a general difference table, yeah, so what this is it's a table that's collated the frequency that's been reported. So in black 0, this value tells you the number of people who have been classified as a typically white sounding CV and with no computer skills reported. Same here, typically white sounding CV with computer skills. Typically black sounding without computer skills, typically black sounding with computer skills. Right. And the first thing we want to notice is that in terms of percentages, and that's what we want to work with, percentages, there is a difference reported. You have 19% of typically white sounding people with no computer skills, as opposed to 16% in the group that identifies as black with no computer skills. There is a difference there, 19 minus 16. Same with computer skills, or same with the group that have reported computer skills, 80 minus 83. And the reason why we can't just conclude that the differences are significant is because we don't know. We have not tested it against anything yet. We don't know what our means are, we don't know where the statistics generally lie. And that's why we need to that's why we need to do hypotheses tests. With statistical software, you can generally just specify the test and it'll do it for you. So what we have here is we've done a 2-sample t-test, testing for differences in computer skills, in the average computer skills reported. And we have to now think about interpreting the data. Right. So how is the t-test computed? First of all, this right here is the raw difference between the means. So in the group that's typically white, this is the mean that we have. And in the group that's typically black, this is the mean that we have. So about 81% of people, of the typically white sounding CVs have computer skills reported, and about 83% have, or 83% in the typically African American sounding group have reported computer skills. And the difference is minus 0.23. with a standard error of that right there. And what we do is we divide this by that. We divide the difference by the mean of the the standard deviation of the difference. And the test statistic we get out of that is right here. And on top of that, what we have is our null hypothesis that the two means, the difference between the two means is 0, right? Now, this test, we test it against a normal distribution, or T with that many degrees of freedom, which is basically normal. And this is less than minus 1.96, right? Minus 2 is minus 2 is less than minus 1.96. And so this test has yielded a significant result, which means that because it's negative, we can pretty much, what it says is that the differences in computer skills between the two groups is significant. There's something to be looked at over there. The process of randomization in this case hasn't worked, which to me, with such a large sample, implies that it's been done intentionally by the researchers. And why it's been done intentionally, we'll conclude later on with the final result that we get. Another thing to note is that if we were testing that the differences were either less than or greater than 0, so over here, what we get is another significant result. What this is saying is that typically white-sounding CVs in this sample have reported on average fewer computer skills than typically black-sounding names. And from that, the general conjecture that we might come up with is that this bias should work in favor of the typically black-sounding names, right? If you have, on average, more computer skills reported on your CV, you should be getting, on average, more callbacks, because that's something employers want in a candidate. Right. This is just general analysis to show you guys exactly why we concluded the way that we did. If you want to read that later on, it's on Facebook. Right. And the next thing we want to do is we want to test for group differences in college. So we want to see whether or not the years of college reported is different between the two. And with our test statistic right here, calculated from these two, we divide this by that. The test statistic yielded is less than 1.96, which means that though there is a difference, an average difference of 0.2%, that difference is not significant. So what we can conclude here is that the process of randomization has worked in this case, right? So we do not have enough evidence to say that the proportion of college attendance between the two groups is different. They're more or less the same. Right. In terms of number of jobs reported on the resume, again, it's quite mechanical, but all you're doing is you're continuously dividing this by that, comparing this to 1.96, and seeing if this is greater than 1.96 or less than minus 1.96. And here, again, we have that it's not greater than 1.96. So we can conclude that the number of jobs reported on average is the same between the two. Right. Again, the test statistic reported, 0.1846, less than 1.96. So with respect to the number of years of work experience, there's no real difference between the two groups. Now, gender is a rather interesting one, because whilst it's not perhaps the nicest thing to think about, we do think that on average, because this is a study undertaken in America, if you have a proportionally higher number of females in one group, what tends to happen is it would work against that group. So on average, we tend to think that the gender ratio has something to do with the number of callbacks that applicants get, or on average. And again, whilst it's not a particularly politically correct thing to think about, it is something that we have to take into account. So, is there a difference in distribution in the two groups of gender ratios? And if we look at it, the difference in means and the test statistic yielded is less than 1, which is less than it's greater than -1, which is greater than -1.96. And again, the statistic tells us that it's not significant enough for us to take it into account in our evaluation. We can move on and say that the gender ratios are more or less equal between the two. Now, and finally, in fact, before we move on to this, let's think about what we've gotten so far. In terms of gender, years of college, and number of jobs, years of work experience, all of these groups seem to be more or less the same. The process of randomization in terms of those characteristics has worked out for us. We've got essentially two groups that are equal. We can compare, yeah.
Was ethnicity the only independent variable this study was looking at, or was it looking at the impact of all of these factors?
Right, that's a good question. In any randomized control trial, you have to separate out what you think is the causal variable, or set of causal variables, and a set of things that you want to control for. When you're doing a randomized control trial, you have an idea about what your causal variable is, but you also have to think about what factors you need to control. And that's why we go through the process of testing those things. These are all what we call control variables. They're not things that we are explicitly studying, but they are things that we think will affect both the outcome and the treatment, right? So that's where selection bias comes from. Yeah.
In the study, though, there weren't the samples. Were they real people, or were they generated CVs that they made up?
Fake CVs.
Okay, so they,
Yeah.
in theory, could have like the fact that we're concluding that there's no significant difference in like gender ratios, for example, or in level of literacy, education. That's something that they actually had control over. So I'm assuming that it would be. Yeah. Okay. It's kind of likely that that would be the case.
Well, you might think that, but most of the time in samples this large, just to save time, you would do it completely randomly, and you would trust that the process of randomization comes up with it. If they had gone about actually constructing each CV in that manner, like looking at the proportions both ways, then you wouldn't have gotten any differences. We wouldn't have concluded insignificant differences. We would have said, look, in each case it's 0. The fact that there are some differences implies that they didn't go about constructing each and every CV in that manner. But the process of randomization has worked out in that way. Yeah.
Yeah, it just seemed, it kind of undermines in my head the purpose of the study of if we're having these as control variables, though, because in real life there will be differences, and probably significant ones, between like whether or not you're black or white. So it's interesting. I mean, do you think that that undermines the conclusion at all?
No, because what we're looking at is a causal relationship. We want to see if either having a black sounding name or a white sounding name is the only factor, or sorry, is a causal variable in affecting callback rates. Whilst all of these things will affect whether or not they get callback rates, we don't want these things to interfere, basically, in the rates of callback that we observe. If we let them interfere, then we're including selection bias in the mix. Do you get what I mean?
Kinda, I'll keep thinking about it.
Yeah? Yep.
Yeah, just 2 points I want to make. One is that in terms of randomization, one of the reasons why, as people, we don't construct it is because people are usually terrible at actually constructing things equally.
Yeah.
And what ends up happening is that if you ask, for example, people to list 10 random numbers, more often than not, they will not be random, and you can pick up some sort of systemic pattern in it. So it's better to do it through almost like a coin flip or something.
Yeah.
Yeah, but in terms of your question, in terms of the issue we have, if you have a question of is there racial discrimination, people can always counter-argue saying that no, maybe people are just picking it based on education levels, because in the US you do see a systematic.
But we've got selection bias in terms of the levels of education. We want to say controlled for the levels of education, the number of jobs. There still seems to be racial discrimination. Or perhaps it is possible to report an insignificant finding. You can conclude that we can't accept the hypothesis that there isn't, but there doesn't seem to be any evidence. But we'll get onto that when we look at the actual conclusion. The one thing I want to turn your attention to is that with the computer skills, we did find a significant difference. And the difference that we found, we would assume would work in favor of the typically African American sounding CVs, right? So basically, we found a significant result that CVs with black sounding names have on average higher computer skills reported. But if we look at the actual callback rates and the percentages that we get from there, the average callback rates that typically typically white sounding names get, minus the average for the typically black sounding names, is positive, which means typically white sounding names on average get higher callbacks, right? So this right here says that on average there's about 3% higher in favor of the typically white sounding names. So right there we have a little bit of a, ooh, what's going on? Well, we can't conclude that it's significant without going through the process of testing it. So we take the difference divided by the standard error, as we've done continuously. And this one's a rather funny result, because that is, if you conduct any test and get a t-statistic of more than 4, regardless of your significance level, that is a significant result. Anything north of 4 is like 100% significant. So what we're saying is that there is no margin of error here that would make this an insignificant result. Regardless of what significance level you assign, this is significant. The average callback rates for white sounding names is higher. There is no margin of error. There is no doubt about this.
Is that the p-value then?
The p-value is 0 in all cases except that one. Yeah. This is quite rare. It doesn't always happen. So this is saying that almost definitively we found a section of the population of employers where discrimination does happen with respect to names. Now, why might we think that it's not just significant, why might we think that there's something else in the mix here? Well, we got back a significant result in another test where we tested for computer skills. And the reason why I said that we have to think about it when we evaluate later on is that typically black sounding CVs reported higher computer skills, and that didn't work in favor for them at all. We got back a result that would be significant regardless of the margin of error you assign. Now, and that affects whether or not we can interpret the result as causal. If, in the case where computer skills were equally distributed, we could still make the claim that it's causal. The difference we get in terms of callback rates is caused by what ethnicity the name is associated with. Now, the fact that having computer skills on your CV has no impact on that is saying that in this subsection of the population, we can pretty much assume that there is discrimination. I think the paper concluded that it wasn't the employers going out and actually discriminating against Lakeisha and Jamal, as opposed to Emily and Greg. It was more that employers learn by heuristics, and they look at the percentage of, say, black applicants who tend to have or who tend to have college and things like that reported on their CVs, and they learn from the past as well. And because in the past, usually you would get a lower percentage in the black population, and employers don't always have time to sift through each and every CV, to save time, if they see Lakeisha and Jamal on the title, they would throw out, say, maybe 25% of them or something like that. There are reasons why this happens, and it isn't that, you know, there's out and out racism in the market. It's more, I think the explanation they came up with was more a heuristic understanding. Right. And the power behind this is that we can actually make a causal claim here. We can say that regardless of all the other factors, because we've controlled for them, the only difference reported is whether or not the name is of one ethnicity or the name is of another ethnicity. And because there's a significant difference in callback rates, this is causal. The difference in callback rates is caused by which ethnic group your name is associated with. On average, black-sounding names on CVs will tend to get fewer callbacks. And this points us in the direction of policy recommendations. And if I'm correct, they've started doing name-blind applications to universities in the UK, and perhaps this had something to do with it. Who knows? Right. We've gone through this.
Sorry, a quick question. In the statistics table, what was the interpretation of the mean that came out? What was the percentage impact of P?
Of what?
Like, what was the coefficient in front of the dummy variable for black, and what did that?
Oh, as in the regression coefficient.
Yeah, and what was the interpretation? Was it elasticity? So was it like 3%? You're 3% more likely to be rejected if you have black.
I don't know, because we didn't do the regression for this one. It was just raw mean comparisons. Do you get what I mean?
Oh, okay, kind of.
Yeah, it was just testing for significant differences. It wasn't likelihood comparison. Yep. Right. So whilst randomized control trials do help us in terms of separating out or isolating causal effects and dealing with selection bias, they're not perfect. They come with their own issues. So one of the first, or the most mundane ones that comes up is cost. In any randomized control trial, you're going to have to take away the individual's ability to choose their treatment. And this doesn't come cheap. So if you're doing a health insurance trial, for the portion of the population that are assigned either insured or not insured, you're going to have to pay them to take that policy. For a lot of the people who would have been insured, they're not want to go uninsured without some recompense, without some compensation. And if you're doing this in a sample of, say, 5,000 like this one, those figures are going to add up. So randomized control trials tend to be quite costly. Another one is the issue of playing God. Right, so in a randomized control trial, the treatment being examined often has an impact on either the individual's health or their livelihood and things like that. Right. And even if the assignment is done by some completely random algorithm so that the researcher can stand back and say, look, I haven't tampered with it. I haven't assigned people treatment based on any personal relationship with them. In the case of health insurance, if one of the sample elements, if one of the individuals involved suddenly falls terminally ill and happens to be uninsured, what do? You know? So in a lot of cases, randomized control trials can be inappropriate. In terms of the study that we did, or not the study that we did last week, or the thought experiment that we undertook, changing someone's university placement, if we find a significant effect in terms of incomes, that you've altered the portion of the population. You've altered the potential income of the portion of the population that were assigned the lower ranked university in a way that's unchangeable. You can't change that in the future. They're going to earn lower incomes now because you conducted this trial. There are a lot of ethical questions that the researcher has to contemplate before deciding whether or not a randomized control trial is appropriate, and this is one of them. Are you altering people's lives in a way that's completely unchangeable? Right. And yeah, so these are all examples of where this issue would be applicable. Oh, a big one is drug trials. One of the biggest applications of randomized control trials is in the medical industry, in the pharmaceutical industry, sorry, where you're trying to test for whether or not a drug actually cures a certain disease, and you have to offer people, or you have to collect a sample of individuals and offer some the drug and some a placebo. If this drug is actually life-saving, you've potentially just shortened the you've shortened the potential lifespan of the people who fall in the placebo group. Yeah, these are all things that need to be taken into account. And there are other more subtle problems involved. In a randomized control trial, even if you've randomized assignment, at the end of the day, once the assignment process has been completed, oftentimes the elements will know what treatment they've been assigned. In a health insurance trial, for the people who would have been uninsured previously, who are now insured, does this alter their behavior in a certain way? Do they go out into the world and take more risks? Do they engage in more risky behavior? Does one of the previously uninsured people suddenly go bungee jumping just because they can? Things like that. I'm not entirely sure. I think Manav would know better because
is this a name when
It's like, this is some kind of bias that has a name.
So actually the bungee jump example, I don't think that would exactly work because that could be a cost of having health, like normal people with health insurance might do it because they have it.
Yeah.
But it would be this, we normally call it an independence criterion of the treatment, which is a very mathematical term, and I don't think it would make intuitive sense.
But it's just something you have to think about when you're doing your trial. Right. And generally, RCTs, right, RCTs do help us to separate out causal effects, but they come with their own problems. And in many social situations, they would be undesirable. But this doesn't mean that the econometrician or the social scientist doesn't have any other tools. There are other tools to deal with selection bias and come up with causal claims. Just in a lot of cases, RCTs wouldn't be appropriate. But does that mean that they're completely useless, even in cases where you cannot run them? Turns out, not really. Dealing or understanding the theory behind a randomized control trial helps us understand where selection bias comes from. It's basically the fact that you're in the real world, if you go out and take the usual averages, you're not comparing like and like. It's not what we call a ceteris paribus comparison, all other things kept equal. And this, in turn, helps us to think about helps us to think about what tools would be appropriate in this manner. Regression, which is next. Right, so before we go, with respect to the hypothetical that we did last week, in terms of education, can anyone think of, besides the ethical question, why it would be inappropriate to run a randomized control trial? In the real world. So not one where you're restricted to 2 universities. It's rather trivial. No?
Universities wouldn't accept it or wouldn't want to be involved.
Or even if they did, there are hundreds and thousands of universities out there. So restricting yourself to a thought experiment with 2 helps you to think about what troubles you might run into in terms of comparisons, but doesn't really help you in terms of thinking about what would separate out a causal claim. Now, if you know that the problem is that you're not comparing like and like, this then leads on to what econometricians call matching, where within groups of universities, you select ones that are similar in terms of entry criteria, either ones that are highly ranked and low or lower ranked, and you compare people within those groups who applied to both, got into both, but for some reason or the other chose to go into different ones. And this is what we call matching, where we take individuals who basically have the same background characteristics, but chose their treatment completely independently of them. And then we compare the in-group averages. And because we're comparing like and like, we can say that this is causal. And the way to extract the causal effect is through the tool of regression, which you guys will be doing next week, right? So this is the end. The slides are all up, and I know I skimmed over some of them, but that's because I talked about the details that I wrote about later on in some of the slides. But if anything is somewhat unexplained, or if anything is still confusing, look at the slides. If that doesn't clear things up, I'm always available to explain things. Right. Thanks for coming to the lecture. I guess that's the end.